Today we have our speaker, Filippo Valsorda. He's a crypto engineer and he's specialized in Go. He's some kind of Go wizard, so to say, and he used to work at Cloudflare. He actually shows now today in the talk how he made an attack to exploit a bug in the implementation of the elliptic curve P256 in Go. That's why he's a Go wizard. And the reason is actually due to a misplaced bit on the assembly level, just due to the curve's implementation. And the result is that you can, in certain cases, you can retrieve the private key in the elliptic curve Diffie-Hellman encryption scheme. So please welcome Filippo Valsorda to his talk. Give him a round of applause. Thank you very much.
Thank you. Thanks. I love the term crypto gopher. Tony came up with it, and I want business cards with that on it. Anyway, okay, I'm Filippo. As you heard, I worked on internet infrastructure, I work on Go, I work on cryptography. But this is a collaboration with Sean Devlin. You might know him as one of the authors of the Crypto Pulse or the Matasano Crypto Challenges. So, a few months ago, earlier this year, a Cloudflare engineer was scanning CT logs. CT logs are big logs of TLS certificates. And it was checking the ECDSA signatures on these certificates. And one of the signatures was not verifying, which is weird because CT logs check the certificates before adding them to the logs. It turned out that the bug was in the code that Cloudflare was using to verify the certificates. And more specifically, it was in the Go standard library. It was in the implementation of the NIST P256 curve, which is a popular, very hard to implement elliptic curve that is used, for example, for ECDSA TLS certificates. This curve has an assembly implementation in the Go standard library to, of course, to squeeze every bit of performance out of it, and specifically optimized for x86-64 architecture. So that's where the bug was. There was a carry propagation bug. It was reported upstream, and everyone agreed that this was not obviously exploitable. But Adam Langley also said that it would be a cool paper, though. And, well, I mean, how do you pass on that? So Sean and I meet in Paris and spend a weekend and then some eating Thai food and staring at this assembly code to try to understand what is it doing. And 1 month later, we have a CV and 2 Go security releases. We found a way to go from this single carry bit bug to a full key recovery against protocols that use elliptic curve Diffie-Hellman in ephemeral static way. If this means nothing to you, it's OK. I will try to go over it. One of these protocols, for example, is JWT, JOSI, or however you want to call it. It has 15 different acronyms. And it's often implemented in Go. So this was exploitable against real-world services. So let's start by looking at the code with the bug. Let's take it from the beginning. This is the short assembly function that does subtraction. When you do elliptic curve math, you usually work on a field. You work on math modulo some prime p. So if you do a subtraction, you do a minus b modulo p. And this is what this assembly snippet does. It sets a to a minus b. Of course, these are numbers way too big to fit into a single register. So how do you do math when you can't fit it into a single register? You do multi-precision math. And the thing is, you all know how to do multi-precision math. You learned it in elementary school, when you would write numbers in columns, And you would do math with register size of 10, because every digit you would subtract 2 digits and carry the -1 if it went negative, and then subtract with the carry and then carry the -1. That's exactly what this is doing. But it's doing it instead with digits, with 64-bit registers, because this is a 64-bit architecture. So we look at the first lines. The first lines is nothing else than subtract, subtract, subtract with carry, and then the carry is finally stored in that mul0 accumulator. But then what do we do if it goes negative? We said that this is modulo p, so we can't just let it wrap around modulo 2 to the 256, because that's how wide 4 registers are. But since we're doing arithmetic modulo number, we can just add that number and the result is the same, right? Adding p modulo p is a no-op in the result. So that's what this code does. It does a equal a minus b. It takes a copy of the result and it adds p. And then in constant time, it uses that final carry to check if it went negative or not, to decide in constant time which one to use. The one with p, so a minus b plus p, or a minus b. And that's subtraction. Straightforward enough. Now, the problem with this code is that if you look closely, you can see something that might be weird if you're not familiar with assembly, still trips me over. To use a condition, like these constant time conditionals there, which have to be constant time because you don't want to leak timings based on the size of the number, you have to first operate on mul0 so that you set the flags, the 0 flag. So normally what you do is you either add 0 or end 1 to your mul0 to check to set the flags. But that's not an add. That's an add with carry. It means that it's adding 0 to mul0 and the carry bit from this addition here, which has nothing to do with it. It's not supposed to be there. Like, this is adding p, but it doesn't matter if it overflows, because if it does, it wasn't going to be picked here anyway. So it's adding another bit into the operation that wasn't supposed to be there. So it's flipping the result. But then, also, the conditions here are flipped. So essentially, it evens itself out. Except when that carry bit happens not to be set, because the a minus b is small enough that if you add p, you don't wrap around. That happens once every 2 to the 32 times, which is why it's so rare that nobody had noticed so far. So the code went in, and nobody noticed for a long time until Cloudflare started scanning CT logs and had this weird one signature that wasn't verifying. And they were lucky enough to actually have it in the logs, because, if it happens transiently, you might just think, I don't know, the connection broke, right? So this is what we call a carry propagation bug. Carry propagation is that activity of making sure that you carry the one. And here, it's a bit weird. We didn't forget to carry it, but we carried a carry. We carried a carry, sorry. We carried a bit that we weren't supposed to carry into a result. Most of the times that goes well, sometimes that breaks. When that breaks, wrong result. Wrong result, wrong point computation. And wrong point computation, so what? Like, how does forgetting to carry the one lead to a full key recovery? This is not one of those bugs where, like, buffer overflow. You know what you're trying to do, even if you might have to jump through so many hoops because there might be all these protections. You know what your capability is. You can overwrite some memory. Here, instead, it's not clear what your capability is. So today, I'm going to try to explain that, how we turn this very rare failed computation into a complete key recovery attack. But first, I apologize, but I have to give a elliptic curve cryptography crash course here at CCC. So we've seen the field. Field means nothing else than operations modulo p. Then there are the points. The points are x and y. okay? The coordinates. They fit an equation, which we don't care about. They fit an equation. They're integers, so we can work with them. And we can use them to build a group. A group is one of the core structures in modern cryptography. To build a group, we need a 0 point, a generator point, and an addition over the group, over the points. So we define an addition. Again, we don't care about how addition works. It's just you take 2 points, you add them together, you get a result. It has all the properties that you remember from elementary school addition. It's commutative, it's associative. And then you have multiplication. You don't actually define how to multiply a point, but if I tell you that you have an addition operation, and I want 5 times this point, what do? You take the point, and you add the point, and you add the point, and you add the point. So this is called scalar multiplication. It's doing multiplication by adding repeatedly a certain point. So now we have a group, which is given by multiplying a point, a generator point, a certain number of times, and we have a multiplication operation. So how do we build cryptography out of it? Like, this is all awfully abstract so far. So we build elliptic curve Diffie-Hellman. If you're familiar with normal Diffie-Hellman, you will see something snap at some point. The private key is a giant number. This is important. The private key in ECDH is just a random giant 256-bit number. And then we have a public key. A public key is that giant number multiplied, the scalar multiplication we just talked about, by a generator point. If you know normal Diffie-Hellman, this is like doing g to the a. If you don't, it's okay. This is just multiplying private key by point. And then when I have my private key and my public key, you send me your public key. We need to agree on a shared secret. How we do that is that I take your public key, which is a point. I take this, and I multiply it by my private key here. So again, it's my giant number private key multiplied by your point. That comes together. The two results are the same, because if we do like my private key times your private key times g is the same as your private key times my private key times g. That's commutative. And we land on a shared secret. And that's all we need to know about elliptic curve cryptography to exploit this. However, there's one thing that I glossed over. It's easy to multiply by 5. You add 5 times. But if I'm asking you to multiply by a 256-bit number, you can't add 2 to the 256 times a point, right? So what do we do there? Remember that here what we're trying to do is the multiplication, the private key times the public key, the point. We do something called double and add. We take our private key and we string it out like bits. And we start from the most significant bit. This is little endian, because I had gotten the slide wrong the first time. But, you just claim that you meant it to be the opposite endianness. Anyway, that's the most significant bit, the one that is worth 2 to the 256. Nope, 2 to the 255. If you flip it, you're adding or removing 2 to the 255. So you start with 0, that's Z, 0, nothing. And you check the first bit, the most important bit. Is that set, yes or no? Yes. So you add the point. Q is the point we're trying to multiply by this giant D. So we add the point. And then we move down one by doubling. Can you imagine how we double something? Remember, we only have addition. We add it to itself, of course. So we use addition to double the point. And you might see where we're going with this. We double every time we slide down one bit. By the time we arrive at the end, how many times did we double that first point that we added because the first bit was 1? 255 times. that bit was worth 2 to the 255, so at the end, that will have the value it was supposed to have. And we keep going. We check if this bit is 1. Is it 1? No. So we do nothing. We double again to move down 1. We check if this bit is 1. This bit is 1. So we add the point. So we did add the point, double, double, add the point, double, moving down 1, and we keep going like this. We keep going like this until, well, we have slides, but also until we reach the least significant bit. At the least significant bit, if it's 1, we add the point. If it's not, we don't add the point. And at the end, we have the correct result. And the result comes from this sequence of operations, which at most are twice 255 operations, which is something that we can do concretely. Now, why did I explain this very specific algorithm to you? Because you have to understand this attack, you have to recognize that each key, so each string of bits here, converts into a very specific sequence of operations. Okay, if you change one bit, there will be one more addition or one less addition, and each key has a very specific sequence. In this case, it's add, double, double, add, double, double, and it keeps going. So, back to our bug. If you spaced out because we took a lot of crypto, I saw a yawn. I saw you. But the two things you should take away are, there's a giant number. It's the private key. We want to multiply the giant number by a point. And we do that by doing additions and doubles in an order that is specified by the bits of the giant number. That's what you need to have clear, the only thing. So let's go back to see how we use that to turn our very small carry bag into a complete key recovery attack. First thing we do is we bubble it up. That function that breaks is called P256 subinternal. That's the function I showed you earlier. P256 subinternal is used by P256 point add, which is what we spoke about, adding to points, the only important operation. And adding to points, we've seen, we use when we're multiplying, when we're doing that scalar multiplication, which is d times q, d times the point. And how is scalar mult used? Here we finally surfaced to a level that if you work with like cryptographic protocols, you might start recognizing pieces of. Scalar multiplication is the operation that the peer does in elliptic curve Diffie-Hellman. There's a scalar, which is the secret, which is the private key. There's a point, which is the public key of the other person, which might be the attacker. So the scalar mult here, speaking in InfoSec terms, has an attacker-supplied point and a secret scalar. And the result, the shared secret, is the session key. For example, TLS. When you open a connection with TLS and you're using elliptic curve Diffie-Hellman, you will do this dance to agree on a session key. If the session key is correct, the connection will open and you will be able to, I don't know, send a HTTP request. If the bug is hit and the result is wrong, so the result bubbles up into a wrong shared secret, the session key is wrong. And the shared session key is wrong, you notice. How do you notice? The connection breaks. So this is what in cryptography we call an oracle. You have an oracle that you can call and send a point, because that's your private key. That's your public key. You're the attacker. And you send that point, and it gets multiplied by the private key, and it gives you one bit of information. Did the bug trigger? Did it not? Most of the times it won't, because remember, this is an extremely rare bug. So you have an oracle that tells you bug happened, bug didn't happen based on the point you send. And let's assume that the key stays the same. We'll talk about that. Can you imagine how we use that to start learning things about the key? Well, let's say that we can magically conjure a point that in that sequence of operation, that's why I told you the sequence of operation was important, the bug happens very specifically at that addition. And we find another point where the bug happens very specifically at that double. If we know already these bits of the key, and we are unsure about this one, what can we do with these 2 points? We send them both. One of them will break the TLS connection. The other one will succeed. That means that the one that broke triggered the bug. The one that didn't break didn't trigger the bug. And we know which one corresponds to which key, because we magically made special points that only break very precisely at that point of the computation. Okay, so we learned a bit of the key. In cryptography, as soon as you learn one bit of the key, there's probably a way all the way down. So we build what's called an adaptive attack. Let's say we have these bits, but we want to learn these 2. We compute 2 points, one that breaks when the addition happens exactly at that point in the double and add procedure, and one that triggers only when the add doesn't happen at that specific point in the double and add sequence. We send them both. Only one of them breaks the TLS connection. Well, then we know a bit. We go back, and we go back to our magic point generator, and we generate 2 new points. This time, we don't look for things that break here. We look for things that break here. We make 2 points. We send them both. One of them breaks the connection. The other doesn't break the connection. We learned one more bit of the key. We go back. We make 2 points. We send them both. One breaks the connection. One doesn't. We keep going like that. Once for each bit. Every time we go back, and we adapt to what we learned so far. That's why it's called an adaptive attack. We can't pre-compute all these points. We have to come up with them while we learn the key. And the beautiful thing about adaptive attacks is that they look exactly like Hollywood. It's beautiful, because you see them flipping and like going through values, getting it right, and moving to the next one, which you all thought it was fake. It was not. Everything else is fake. Not Mr. Robot, that's good. Anyway, okay. So, this attack, we came up with it. We thought we had something extremely novel. We went to the literature, and everyone that has picked an academic career in the audience knows exactly what happened. We found a paper that was doing exactly this. However, it was a little different. It was still P256, and it was still ECDH, and Okay, it's really similar, but it's an attack that depends a lot on the implementation details, how you pull it off. You can't suddenly just repurpose the code. But the idea so far, an adaptive attack where you send 2 points and you check which one breaks, is the same as a BBB paper from a few years ago when it worked against OpenSSL instead, instead of against this bug in the Go standard library. So instead, from now on, we're going to talk about how exactly we implemented this against Go, because this changes a lot based on the implementation details of the library you're working with. So this was the general idea of how the attack works. All that you find points that break at the right time, you send them both, and that way you learn a bit of the key. Except I lied to you. I lied to you because I lied to you on a lot of things. The first one is that Go doesn't do double and add 1 bit at a time. It does it 5 bits at a time. It's called booth multiplication. It took us forever to figure it out. It's an 80s paper. Instead of adding 1 point or 0 points and then doubling, it adds between minus 16 and plus 16 points, and then doubles 5 times, moving down. It just does it in blocks of 5. Okay? So it splits up the key and then looks at each block of bits, picks a value from a pre-computed table, which is just all the values from 1 times the point to 16 times the point. And in the loop, it doubles 5 times because it moved 5 bits down. And then it chooses which point between 0 and 16 to use from the table, and it adds that to the rolling result instead of adding 1 or 0. There's also a bit of constant time arithmetic there, because the other thing I lied to you on is that there's no such thing as a 0 point. It's an imaginary point that we add to make the math work, but when you try to tell the code to actually add the 0 point, it's like asking it to divide by 0. It just won't do it. But you know how you add 0, right? You do nothing. So there's some constant time code here that looks at it, and if it's 0, it does nothing. If it's not 0, it adds the value. So the first thing we had to do to adapt to this format is that we worked in limbs. When you hear me say limb, it just means that we will look at each 5-bit block on its own as its 0 to 16 and sign value. That's much easier because it's actually kind of weird how the 5 bits are extracted, and I don't want to bore you with it. So let's just consider that we look at each group of 5 bits converted into a value from 0, 16, and a 1, and a sign or a plus minus 16. So when you hear me talk about limbs, you just know that it means the 5-bit value from the key. This is still the giant D key that's the multiplier. So how does the attack change? Not that much. Instead of attacking 1 bit at a time, 2 points, one that breaks for 0, one that breaks for 1, we attack 1 limb at a time. One that breaks for 1, one that breaks for 2, one that breaks for 3, 16, minus 1, minus 2, minus 16. So to move 5 bits, to recover 5 bits of the key, we will need, on average, half the space, 17 points, which is a little less efficient than the bit-by-bit one, because that would be 5 points for 5 bits. So, however, how the attack triggers is the same. We're looking for a bug that happens in the 5 doubles at the very right time, or that happens at the addition at the very right time. Now, that's still the high level of how we're going to do it. But in practice, I didn't tell you how we're going to magically generate these magic points that break just at the right time. And I didn't tell you because it's fuzzing. There's no specific way to generate them algebraically. So instead, we just hooked the assembly code with something that would just set a Boolean, true, false, if the conditions for the bug are met. And then we run through a lot of points. And for each point, we run it through the limbs we already know. Remember, this is an adaptive attack. So we want to learn the next limb. We learned a few limbs, we want to learn the next one. We run through the ones we know, and then we try all the possible values for the one that we don't know. If one of them, and only one of them, breaks, that's a useful point. Because if we send that point and it breaks, we know exactly what the value of the next limb is. Okay, so this is going even more low level. If you're interested in optimizations, we had to run through a lot of candidate points. And for each point, we needed to know the D value, because we can find a magic point, but if we don't know the private key, we don't know if the entire protocol works, and our oracle doesn't work anymore. So to work with that, instead of multiplying a new random private key every time, we just added 1 to the private key and added added the point to the public key. This is just an optimization. We called into the various assembly of the standard library. Don't do this, but it's beautiful. You can go call all the unexported functions in the standard library. I will never approve it on code review, but I love it. And then there's some post-processing to make sure that the bug is actually there, because sometimes there are false positives. So we just run it through the broken code, the fixed code. Is the result the same? Well, false positive. Is it different? No, good. Okay, so we have a beginning. We have a way to move through the attack. The only thing we don't have yet is how we figure out the first limb. The first one, the most important, the most significant one, when we still don't know anything about the key. The problem with this one is like this. So let's pick 3. It's an example, okay? Let's pretend that the limb is 3. So we do our usual thing, we do our fuzzing, and we find something that breaks at the 5th doubling. And we send it, and it breaks. It means that the first limb is 3, right? Wrong. Sadly, it might mean that the limb is also 6 or 12. Because how 6 is selected, for example, is that 3 is taken, it's doubled, and saved in the procomputation table as 6. Then it's taken out of the table, doubled 5 times. But what happens after you double 6 4 times? What's the value? The exact same as doubling 3 5 times. And the sequence is the exact same. So we don't know which one it is, because we only know that that's the sequence, but that doesn't tell us anything. And the same happens for 12. 12 is nothing else than 3 double double. So if we double it 5 times at the 3rd double, it breaks. And we only know if it breaks or not, so we can't move. So instead, what we do is that we find 3 points. One that breaks after doubling 3 5 times, one that breaks after doubling it 6 times, and one that breaks after doubling it 7 times. We send them all, and we look at which ones break. Only this one, it's a 3. The first and the second, but not the 3rd point, it's a 6. All 3, it's a 12. This took me forever to wrap my head around. This is like pure Sean insight. Okay, now I can feel that you're getting a bit tired. This is intensive. There's a lot of math, so let's go for a change of pace. And let's talk about kangaroos instead. I'm going to tell you something that I learned from a cryptographic paper, I swear. And it's about how kangaroos jump. Apparently, kangaroos jump depending on how the terrain on which they're starting, on which they're jumping from, is. Depending on that terrain, if you put 2 kangaroos on the exact same spot, they will jump the same distance and approximately the same direction. I don't know if this is true, but Pollard said so in a paper, and I am not arguing with Pollard, so. Now, why is this useful? Well, this makes for an extremely cool way to catch kangaroos. I mean, did you expect some math or crypto? No, we're catching kangaroos here. So you take a kangaroo that you have on hand, because you all have a kangaroo on hand, and you put a GPS tracker on it, and you let it loose. This kangaroo jumps, okay, and it roams, it enjoys a brief stint of freedom, and it runs. And at some point, you go pick it up, and because you know where it is, and you place a trap there, exactly where you find it. What happens to the kangaroo that is just passing by? If it steps at any point on one of the points where the other kangaroo jumped, from there on, it will follow the same path, because each jump depends on the ground. So this way, if the wild kangaroo lands on any of the prints of the previous kangaroo, you're catching it, because eventually it will end up in the trap. Okay, so this had nothing to do with the talk. I just wanted to share this. Now, okay, so here is how this converts to crypto. We can make elliptic curve points jump like kangaroos. We just have to make the jump deterministic based on the input, based on the starting point. For example, we can take a hash, any hash. You design the hash. Apparently, that's popular in cryptocurrencies to design your own hash. Okay. And you hash a point to another point. And when you want to do a jump, you take the point and you add it to its own hash. So qn plus 1 depends only by qn. And this is just like the kangaroo jump. How do you use this for what we're doing? We want to recover d, right? We want to recover the multiplication, the multiplier, the discrete logarithm, it's often called, of the public key. How we work with this is that we take a tame kangaroo, a point that we know the d of, and we make it jump a lot. Keeps jumping. And we remember what the value is at the end. We take that value at the end and we save it. No need to keep all the points in between, so we don't need some giant memory construction. And then we take the point that we don't know the d of, and we make it jump a lot. What happens is that it has much higher probability to intersect one of the various prints of the previous point. When it does, it will eventually end up in our trap. It will end up having the same value as the one we calculated earlier. When that happens, we know how far the wild point traveled because we were the ones making it jump. So we can just walk backwards to the starting point. It turns out that this is extremely efficient to find the d value when you know the interval of the d value. The intuition there is that if the kangaroo starts in a small area, you know when it's been too much time, it probably traveled past your trap. So you have to rewind time, which in crypto you can, and try again because it went past your trap. So the smaller the interval, the more precise you can be, the more efficient the attack. This is called the pollard kangaroo attack. And it's described in an original paper from the 80s. It was described on Diffie-Hellman first, but it works on any groups, so it works on elliptic curves. And the elliptic curve version is then improved by a few papers later. And there's a chapter in the elliptic and hyperelliptic handbook that describes it. So we have it all. We have how to start, we have how to run through the attack, and we have a how to end. So now let's get concrete. Let's pick a target. As I said, this attack works against JWT. JWT made a lot of questionable choices. One of them is to include as one of the public key algorithms elliptic curve Diffie-Hellman, but not the version of Diffie-Hellman you and I are familiar with, the one where we both generate a new private key every time, which makes this attack impossible. Remember that this is an adaptive attack. We need to query the oracle for the same private key over and over and over again. Instead, there's a variant called ephemeral static Diffie-Hellman, where one of the two sides is always the same. This is sometimes done as an optimization, don't do that, OpenSSL was doing that, and it stopped doing that after a bunch of attacks came from that. So in TLS, that usually doesn't happen, and the Go TLS stack thankfully never did that, so the attack doesn't work against TLS. But JWTs encoded it straight into the standard, because if your public key is fixed, so is your private key, always the same. So if we have a service that accepts things encrypted with a public, with a ECDH-ES algorithm, we can use this attack, for example, against the popular implementation Go Josie. It's not Go Josie's fault. And Go 1.8.1, the latest vulnerable version. And we can just check if the service can decrypt what we're sending it. It can be because it throws a HTTP error when it can't, because of different timings. This changes in any case, but what you need is an oracle that tells you, did it work? Did it not work? Did the bug trigger? So are you right about your prediction of the limb, or are you not? Then, of course, we need to do a lot of work. If you don't have the resources of big corporations of where to spin up things, you can just use EC2 spot instances. How we architected that is that there would be a small piece of code that would do nothing intensive on your laptop or anything that would accept HTTP requests from the workers. The beautiful thing about this infrastructure is that you can horizontally scale the workers, spin up as many as you want on non-heterogeneous platforms, because the only thing that they need to be able to do, they don't need to have ports open, you don't have to worry about NAT, you can even run it on your botnet, because the only thing they have to do is connect back and ask for work. And then after 30 seconds, or when they find a point, connect back and say, I found something, I didn't find anything, give me some more work, and send the result. This was also useful because if you get the worker code wrong, or if you want to change the deployment, you can just redeploy the workers without losing state on the dispatcher, because the dispatcher just keeps running, and it will just wait for workers to come and ask. Specifically, we built this just with the small script that you can start an EC2 machine with, because we didn't even need to make a custom image. So a few figures, a few numbers. Each key has 52 limbs. It will take a bit less than that because we have kangaroos, but let's say approximately 52. Each limb is 16 points on average. It would be 17, but 2 of the points are faster to fast. So let's say 16. Each point takes approximately 2 to the 26 candidate points. So we have to try 2 to the 26 points before we find one that triggers the bug at the right point. And since we need 16 candidate points and each takes 2 to the 26 candidate points, that takes approximately 85 CPU hours. That's like one CPU running for an hour, one core. Turns out that you can get 85 CPU hours from spot instances for about $1.25, which makes the total cost of the attack something like $60, which was a relief because I had done the math wrong first, and it came out as at 1,000, and I ran the demo tonight and I didn't check the bill. Yeah. Anyway, it's cheap. Now, I am not brave enough to run the attack live, because yes, it's a nice infrastructure, but no, I don't trust it that much. But also because it takes a while. Like, if you don't want to spin up infinite number of EC2 machines, you have to accept that it would take about, I think, our attack run in 12 hours. So we're going to look at a sped up version of a 1-hour video in the next 45 minutes. You have time, right? No, it's a couple minutes. So this is the UI. It shouldn't be too confusing, and if anyone works at Hollywood and wants to license it, we can talk. What you're seeing is that the red values are the ones that we found a point for from the workers, and we submitted. And when we submitted it, it resulted not to be the right limb. And the green ones are the ones that instead broke, so they're the right limb. Remember that here the target is a JWT receiving application. And then you can see the key slowly flipping from the bottom, and it's exactly like Hollywood. I love that. So yeah, you can see the limbs filling up as we find them, and that approximately there's 30 bits, so 2 to the 30 rounds, 2 to the 30 candidates work for each round, for each limb that we find. It obviously depends on luck. So, and yes, the thing will probably keep running for a little while, but this is already at limb 9. It has to get to 52, and you don't have that patience. So this was the attack. The code will be open source soon. Leave the limbs you lost. They belong to us now. And any questions?
Valsado, thank you very much for this lovely talk, and the kangaroos. So we have a question from the Signal Angel. Go ahead, please.
Actually, the internet wants to know, did you compare this bug to implementation in other libraries?
So I guess that means if I looked for similar bugs in other implementations. We did not, also because each implementation is a bit different. Hanno works on a lot of fuzzing of big-int implementations, and he asked me, on Twitter just today, if I tried fuzzing the Go implementation, for example. And sadly, this is constant time code that is specific to P256. So the answer is, there's a lot of them, and the bug can be small and anywhere. It's not like you will be looking for another bug in P256 subtraction. It can be anywhere in the underlying math, and we can turn that into the same attack. So no, we didn't look for this specific one, but I think that 4 CVEs in 2017 on OpenSSL have descriptions that are very similar, but they're about finite field Diffie-Hellman, like normal DH. If you look for something that says about it's barely doable because all the computation can be done offline, that's this kind of attacks on OpenSSL. Next.
Are there any other questions from the Signal Angel? So please line up at the microphone. Microphone 1, please.
So why can't you determine the points algebraically?
Laziness? No, so it's entirely assembly, and there's a lot of points where the value is then thrown out, or it might get corrected by how it's essentially. We didn't see a clear path to this, and it's $65 on EC2. So it doesn't really change the feasibility to just fuzz them. So we just went for the fastest path to the entrance.
Are there any other questions?
No one is asking about kangaroos, people. I mean...
Yes, ask about kangaroos. It would be lovely. Have you been to Australia?
I haven't.
Okay, you have to.
Yeah, definitely.
I think there aren't any other questions, so give Filippo Valsado a big round of applause, please.
Thank you.
Thank you.